everybody, we made this, which is a wind turbine based on a sycamore seed, or as we used to call them, spinning jennies. The group name for them is a samara seed. But it worked quite well, I thought. In the video I pointed out how similar this was to the shape of a whale fin, particularly a humpback whale, with the exception of the leading edge being covered in little bumpy bits, and those bumpy bits are called tubercles. And it does make you ponder whether those tubercles in fact have a function or they're just bumpy bits. The first person to ponder this was a marine biologist called Frank Fish, and with a name like Fish you really have to end up being a marine biologist, don't you? And he asked himself the question of what effect that would have on the whale's ability to swim and turn and be aerodynamic in the water, and he got together with an engineer, an aviation mechanical engineer called Philip Vawt, and they investigated this and produced a paper on it. What they found was the nodules actually concentrate the areas of lift between the nodules and both increase lift and decrease drag, and it's significant in the region of 15 to 20%, which is huge. Of course, what they did was make a patent on it. The patents are funny things, incidentally. One of the things a patent doesn't cover is private use. You can do this as long as it's non-commercial, or you can do it for education and research papers. Patents protect commercial use. So putting it into a patent means for private use, anybody can do this. And that made me think, okay, what about if I stick some of those nodules or tubercles along this shape, seeing as this shape is so much like a whale's fin, would that give me an improvement? And of course the first step is to stick a load of tubercles on, which is exactly what I've done here. Now, of course, I'm going to update the file in Thingiverse and add this as an extra print if somebody else wants to test it and see whether it works or not. But I've printed this off. Now let's print off 3 more and the nose cone. There we are with exactly the same structure, nose cone, 2 of the fins on and a handle, so I can hold it, a bit of steel rod going through 2 bearings, and it's free to spin in the wind. So we put those on in the same way that we put this on in, and we have 2 of those, and now we can have a sort of side-by-side comparison. So to test that, we've come to a hill near where I live because we get a reasonable amount of wind. I mean, there isn't a lot of wind today anyway, but we'll do that test, and the test is going to be pretty simple. We're going to hold the 2 up together in a wind and see which one turns soonest and which one turns quickest, and that'll give us an idea of whether this is BS or not. Okay, I understand that was a little equivocal. I mean, we're standing on a hill with a couple of these things, but there is a lot of research in this already, so some more facts and figures, I guess we can refer to the paper. But as far as I can tell, it certainly seems to have an impact. So we might try that on a whole host of things like this, which is the Ingenuity blade. We could try a load of tubercles on there, or we could try it on just a standard blade setup and see what happens, or we could put it on a VAWT where we put the nodules, the tubercles down there to see if we get an improvement from that. Now, the inventors of this say that it's much broader than just wind turbines. You can also look at things like water turbines. You should get an improvement there, and they say that if you stick it on something like a PC fan, it makes the fan quieter and more efficient. So it's a very exciting development, well worth an awful lot of looking into, should anybody feel like picking up and having a look at that as well and see what we can come up with. So we took this, a sycamore seed, scanned it in, replicated it 3 times and printed out that. Now, it worked quite well, but there are little issues with it. And the issue with it is, if you look here, that blade actually has a bump in it there that's out of line with everything else. So chances are it's going to cause turbulence. I would have liked to have taken that out. And then of course we added the tubercles to it by putting lozenges along the leading edge. But those lozenges, well, they're bumpy, and so without a doubt the airflow over here is a little rough, and of course there's just a gap along the leading edge, and there's no effort to make a little curve in there because I can't do it. I don't have the programming skills to be able to draw that properly enough. Now, the purists among us will say, well, just learn them then, and that's a very valid point. You should just learn them. But I looked at Blender, and Blender is universally understood to have what's called a very steep learning curve, which is just a kind way of saying if you want to spend 2 years of your life learning a program before you can use it, choose Blender. No, I'm not going against Blender. Blender is an awesome program. It's used for millions of things. You can use it for making your own animated films. You can use it for doing 2D drawing. You can make brilliant 3D models. It's awesome, and it is everything to everybody, but it's also very complicated, very scary, and takes a long time to learn how to use it, and I don't want to do that. I'm not sure why that makes me a horrible person, but I don't want to. I want something that's much more approachable, because there are lots of times I'm coming across these little issues that I want to clean up. So for example, this is the Ingenuity blade, and we scanned that, and here at the trailing edge it gets a bit thin for the scan to be able to cope with it, and so it's got little lumpy bits and tiny holes that are basically left alone, and so there are faults with that I would like to rectify, but don't have the programming skills and the drawing skills to be able to do it, and don't really want to spend years learning how to do that. I want something that's intuitive to me, and luckily enough, of course, there is something that's intuitive to me, because there is something called SculptGL. Now, SculptGL is probably the Tinkercad of the modelling world, and it's very intuitive. It takes as its idea, you have a ball of clay. That ball of clay you're able to shove around. Okay, go to a web browser and type in SculptGL, hit enter, and it'll take you here. Now SculptGL, that will start it immediately. You want that one. Click on that one and it will give you the Sculpt page, and here you can see that you can actually download it, because this is a web browser application that works online as its primary source, but you can download it and run it locally if you want to, so you don't have to have the internet. It will still present itself in a web browser. Now, it's so intuitive to use and so easy to use that this will work on your phone, it'll work on a tablet, it'll work on a PC, it'll work on a Mac. It's absolutely brilliant. But if you want to use it in the web, then you just jump to the web-based one, and to get there, just click there, and that'll take you straight in, and there it is. So we go back to our web browser, and here's the first page we looked at, and we clicked on that one, which took us to the home page. If you click on that one, it will jump you straight to the program, and there it is. They're presented in the first opening with this ball of clay. Now, I don't intend on this being a tutorial really, because on the home page, if you look here, you find a set of tutorials at this YouTube channel. Click there, it'll jump you straight there, where there are some awesome tutorials. So I don't intend on going through this. We're going to use it to actually modify our Samara seed blade to something that we want. So let's go straight in there and have a look at that. This ball of clay we don't really want. So if we go to scene, we can clear that scene, in which case it will delete the ball of clay. And there we go, we've now got a blank scene. On the scene again, we can add a sphere, which was the ball we started with, a cube, a cylinder, or a torus, and they're all the lumps that we can actually start with in order to model some awesome model. But we want file import. So we go to file import and add OBJ, SGL, PLY or STL. Those are the files that we can add. If we click on that, it'll take us to the one that we want, and we want Swanky Crift 2, which is an odd name for this, but that's still the name. And there is our Samara seed, the one that we had problems with, and that is the dip that I've been burbling on about. Now if we go over here, then we get the sculpting and painting tools, and really we're going to move this around like a lump of clay, because the first thing we want to do is push that out as if we were pushing it with our finger. So instead of brush, where we're going to lay things on, what we want is drag. So if we hit drag, we'll be able to push that as if we were pushing it. So we go over it and then push it, it will push it out. That's so cool. Equally, if we go here and push down, it'll push it in. Now you'll notice there's actually 2 red dots appearing. That's because we've got symmetry turned on. If we turn symmetry off, then we'll only get 1 red dot that's appearing, and we can push with that 1 red dot on the area that we're actually interested in. I've got the grid showing here. Let's hide that grid. And there in scene, we've got show grid. Let's turn it off, and we've got hide grid. In order to move in and out of this, incidentally, you use the scroll wheel on the mouse. In order to spin around it, then either right or left click, and you can spin around the model by going to different places and just spinning it around. If we want to move the actual model so that we can get closer to it, hold the Alt and then left click and drag. And what we're actually doing is moving camera position, but it looks like we're moving the model. So we can move the model, and then we can zoom in on a particular portion that we're interested in. Then without holding down the Alt, we can spin it around, and we can see how jagged that actually is. To remove that, what we want is the smooth tool, and then we can smooth that area just by painting over it, again as if we were pinching it. That is beautiful. And then we can just smooth those edges to make them nice and smooth. Again, if we go out and we spin around the model a little bit, then if we get a lumpy area, we can choose to flatten it, or we can pinch it out, or we can smooth it, or we can do something called inflate. Inflate is where there's an area that maybe is a bit thin for you. So for example, here, let's inflate that. And then if we hit the inflate on there, what it'll do is act as if we're blowing behind the clay, and we'll fill that area out. And we can thicken up our leading edge by doing that. And if we feel that's a bit too puffed out, of course what we can do is flatten it. And then we keep on doing that, dragging, pinching, flattening, smoothing, just like you would with plasticine or clay to get the shape that you want. So let's do that. Okay, so this bit is actually magical. If we hit the smooth and then we can smooth over the area, you can see all those nasty little lumps and creases disappearing as we smooth it. Now you can change, if you look at that red circle, that's the radius of the smooth brush we're using, and as we use this slider bar here, then we can change the area of the red circle, and that's where the influence of smoothing will be. And this is true for all of the brushes, so we can smooth a huge area. Okay, it's quite addictive, but once you've done that, of course, what you'll get is your rectified STL file, and that's our 3D model that we've smoothed everything out. We've pinched out the trailing edge so it's sharp, we've inflated the leading edge so it's got a bit more of a cut in it, and then we've smoothed all the edges out so it's more like a blade and less like a sycamore, and it's much more even. So of course we can now export it. We export it by saving it as an STL, and there it is saved. Now let's print it. And there it is printed, and it looks very much more beautiful indeed. This is nice and thick like it should be, this is nice and thin, and as this was printing I checked the wing profile and it's much more like an NSCA airfoil than it was here. And we've also taken this drop out here a bit so that we've got a nice curve on there, so very much nicer job. Of course what we want to do now is this one here, which is very lumpy, and of course I've done that, and this is what they look like in comparison. So I want to print this one out and then we'll get a nice look at that, because this one is obviously a bit of a blade in general, and this one is one of the things I want to test. So these two blades, of course I will be putting them on Thingiverse in case you want to have a look at them, in case you want to play with them, but the whole idea has been to use that SculptGL to take out the things that we can't get when we're doing combinations of scanning and modelling, to make them very much more organic in their approach and presumably would perform much better. Now, this idea of sculpting in clay as a process is in fact gaining a lot of ground when it comes to 3D modelling, and the things people are doing with it are just amazingly, well, incredible really, and it is super intuitive. It was, I don't know, 10-20 minutes before I was using that program. It took me an hour to learn how to use the cursor in Blender. 20 minutes later I was producing something in that program, so it's well worth giving it a go and adding it to your armory. Now, without a doubt there's always going to be people who say, why bother, just learn one program, and sure, but the problem with a Blender program, or a program like Blender, is it's just too much. You're just never going to use those things, because all we want to do is smooth out a few curves. We don't want to make a 2-hour animated film of all the characters that we've generated, and for that something like SculptGL is another string to your bow. Here's a hill of clay. Oh, once we've dug our clay out and got it home, we need to do a bit of preparation with it usually, because there's all kinds of pebbles and bits of stuff in there. It's not that difficult. Put the clay in a bucket and add a whole load of water. Give it a good stir with a stick and your hands to break up the pieces so that you make sure you mix everything properly. Then you need to sieve it. Just pour it through a household sieve, and what you'll find is a lot of the bits of stone and stick and all that kind of rubbish just collect in your sieve. Dump it out, leave it a set, and then after you've left it for a day or so, pour off the excess top water, and what you'll be left with is a nice clay slurry. Pour that into a pillowcase, a muslin bag, an old sheet, something like that. Gather it together and leave it sitting around for about 5 days, and the water will drain. Now that might seem like an awful lot of trouble to go to, and to be brutally honest, it is. But there is something very satisfying about taking nature and with your own skill and abilities transforming it into something else. But if you don't want to go through all that mucking around, well, you can buy it, eh? It's not that expensive. Or you could use plasticine if you don't like the idea of using clay. Or I suppose you could use milliput. There's a whole host of things you could use. I've gone this way because I do like that idea of going out into nature and transforming something into something useful. I mean, let's face it, everything we've got is on one stage dug out of the earth. So that's the way I've chosen to go. You may have a different choice. Now then, equally, we have choices again. Once we've got our modelling material, our clay, our plasticine, our milliput, whatever it is we choose, we can build whatever it is we want by modelling it up. We don't necessarily need a computer. If you want to model, then of course there's a couple of ways again to go. One, you can just have a flat piece of something with an armature and build it directly on that armature. Or you can take an existing model like this. This is the Ingenuity blade that we got from NASA, and we can add tubercles to that. We can add the tubercles just by pinching off bits of clay and putting those tubercles onto the surface. So once I've covered the entire surface with clay, I've just put these in to start forming those tubercles, and now what I need to do is make them neater. And for that, use a bit of a stick, my fingers, and some water to smooth the whole thing. So we just go up and down the tubercles, making sure that they look right in terms of a whale. Now if you look at the models that were made, They've been carved out of wood. The beginning of this title is a wooden one. They've been made out of carved polystyrene, carved various bits and pieces, built up from clay, and although they tend to be sinusoidal, actually when you think about the nature of them, then being a bit rough and uneven doesn't actually seem to make that much of a difference, and so we can quite happily sculpt these in. And when we're happy with what we've got, then we can smooth the whole surface just by dipping your hands in some water and giving the clay a rub, and it will smooth everything out for you and make it a nice smooth surface. And when you're happy with it, which is pretty much where I am with this, of course we need to leave it to dry and make some kind of permanent representation. Now of course I've got a scanner, so I'm going to scan this, but we could just make a mould of it, and you'd make a mould by pouring some plaster of Paris around it when it's dry and leaving a split line here, and then you'd be able to make as many as you wanted. So there are lots of ways to make a mould, and to turn it into a permanent model I'm going to scan because I have a scanner. And there is our 3D model of the Ingenuity blade with its tubercles. Now all we've got to do is print it off. Okay, and there it is printed out, and to be honest it's really quite beautiful. Those curves are really smooth. So we've gone from this, the original Ingenuity blade, made this clay model with the tubercles on it, and then scanned it and brought this out, though we could have cast it. Now, for all those who want to point out to me that I could have done this entirely on the computer, well, you are entirely right, but you may have missed the point, because there's a moral to this story. And the moral to this story is that the best way of doing something is always a balance and different for different people, because it's a balance between the materials you have available, the knowledge you've got, the skills you've got, the tools you've got, and your own particular bent for the way that you like to work. There is, in fact, no real best. It's one of those illusions that we seem to believe in. Now, don't get me wrong. I think suggestions on how to improve things are awesome. And there's a difference, though, to a suggestion on how to improve and telling somebody that's the only way to do something. If you're telling somebody that's the only way to do something, well, to be honest, you're wrong, because there's always loads of ways of doing any particular job, and half the time, if people think there's only one way, then of course they just won't try and they'll give up. But there's a myriad of ways. I did this from clay. I mentioned some of the materials I could have done. I've seen this carved out of wood. I've seen it carved out of balsa. I've seen it carved out of pine. I've seen it carved out of polystyrene. There's just so many ways that you can approach a job like this that's usually in the boundary of things you have lying around, but you think there's only one way to do it. So I wanted to illustrate that actually there's a ton of ways of doing something, even to get something like this, which of course is cutting edge science, because these things are the current source of much research and are being shown time and time again to actually make a really positive difference. So I've got this thing, which is a pedestal fan, and I've got it because I want a production fan blade. This must be pretty good at blowing air over you. Now the reason I want that is because I want to compare this. This is our Samara Seed wind turbine blade, and it's supposed to act as a fan. And I remember we covered this in tubercles to make this, and they were rather lumpy, and so we smoothed those tubercles out to make this beautiful shape here. And clearly what I've done is printed 12 of them and arranged them around that fan, because although we're doing it this size so we can get some kind of measurement out of it, if it's right that it's better and quieter, then it would make a brilliant PC fan. But we want to do a quick test on it, so we're going to do some kind of comparison between that and that to see how they do. Now of course this is all on Thingiverse, and of course you can just download it, but there's a couple of things I want to point out to you. This thing, I want it to blow air over me. I want to take the air from behind and push the air out. So it looks like they're reversed, because this bit is the bit that should be cutting the air. So it should be spun that way so it can cut the air and then blow it out. If I twisted these in the other direction, I would have to spin it that way to do the job. So the only difference a twist makes is whether you spin it clockwise or anti-clockwise. And if you want to spin it one way, twist it one way. If you want to spin it the other way, twist it the other way. So in that direction, I need to spin that anti-clockwise when seen from behind to get it to cut the air and blow the air over me. What we need to do is see if we can get a measurement out of that and have a listen and see whether we can find out if it's actually quieter or not. So to do that, what I've done is I've stuck this blade on a bit of steel and I'm going to turn it in a hand drill so I can turn it clockwise or anti-clockwise to see which one might work. And I've got an anemometer and I'm going to put that as close as I can get so it's blowing air over the anemometer and see if we can get a reading out of it. And obviously I'm going to do that with both of them. Okay, that was a bit pants. I mean, I couldn't get anything out of it. It is blowing a little bit of air out at that speed. I mean, the drill speed's really slow. It's blowing a little bit of air out, but I can't say it was particularly impressive. So let's give this one a go. Okay, that was awesomely impressive. I mean, it had no problem at all. You might not have picked up on it, but this was actually very much quieter. I could hear it, but you might not have got that across. It was much quieter, and obviously it was blowing an awful lot more. I mean, people might say, well, there's more blades on that than there is on that. But the swept area is the same, and the area of the blades, if you added them together, I would guess would be more or less the same. But certainly, that arrangement was very more effective than that arrangement in the little experiment that we just set up. Okay, 100% I got the timing on this wrong, because who's interested in fans in autumn coming on winter apart from people like me? I should have done this in the summer, but I would say it was pretty convincing, for me at least, that this addition of tubercles in this functioning as a fan makes a significant difference in its performance, so well worth pursuing if what you're interested in is fans. So we compared that against that, and it was a bit rough and ready, but it certainly gave the impression that that worked better, and a lot of people pointed out that the test perhaps wasn't as fair as it could have been, and they were right, it wasn't. It was an impression. However, we do have this. This is the latest and greatest popular fan blade, the toroidal blade, that is supposed to work more efficiently and quieter than a standard blade. And I've tested this in a fan and it's certainly quieter. So what I thought I'd do is I'd test this with an identical one, but with tubercles added on, because I can print them and can control that. So this one is without tubercles, and I got it from here. And it is basically only 4 parts. There's the 5 parts actually, if I think about it. There's the toroid blade there, there's a foot, there's a cap, there's a body, and then there's this little motor that I got from Amazon that fits right in there. And we can make a toroidal fan without tubercles first. That motor presses into the body, the toroidal fan actually goes onto there like that. It's a little bit of a press fit, but so it should be. And the front will glue on there, and the foot will glue on with the wire sticking out. So I've got it on a 3-volt battery, it's linked up in series, and we're going to read the amps and see how much speed we get out of the airflow. That was 2 meters a second. So that one without tubercles was about 165 or 166 milliamps, and it pushed out about 2 meters per second on the airflow. Now let's give it a go with this one. This one is the same thing, but it is just got the tubercles added, and we'll do the same stuff. We'll set it going, have a read at the amps, measure the wind speed, and see what we get out of it. So I have to keep pausing this so I can go and see that, because I can't see it from my positions. I go and check the numbers. But it was 2.1 meters per second, and I would have said it was sort of 153, 155 milliamp draw while it was running. So it's a lower amp draw. Remember, it's 3 volts throughout. Lower amp draw, and we've got a slightly higher wind speed from adding the tubercles. And I added these randomly. I mean, I just put 4 to each side, really. No, just guess. no idea why. So we got that result from it, which I thought was pretty cool. Now, I don't know if you've noticed, but right when I connected it, we actually had a slightly higher amp draw. That makes me think there's a higher starting torque, but a lower running because of the tubercles, which I thought was really interesting. And it could be why this doesn't actually work very well as a wind turbine. I tested this as a wind turbine and it wasn't impressive results, and that could well be why. But under a constant load as a fan, it seems that that's actually brilliant. It's the toroid shape, incidentally, that doesn't work well as a wind turbine. The tubercles work brilliantly on a wind turbine. So I have put this on Thingiverse. Should anybody want to check what I've done, verify what I've done, repeat what I've done, improve what I've done, it's all there for you. Just download the files and print them off and go at it. But it does seem that that makes yet another improvement as a fan on the toroid shape, and well, it's got to be the ultra fan you were looking for, hasn't it? We've been looking a lot at these things, these bumpy ridges along the leading edge of a fin, and of course this came from Wales. We've been using it in air, but air and water are understood to be fluids. The difference between air and water is that water is a liquid, and that means that it will fill a volume that is equal to its own volume. Air as a gas will basically fill any volume you put it in, but they're both fluids and both behave the same way, and we know these were derived from whale fins, so we should be able to use these to extract energy from water. Now, traditionally, there's basically two ways of doing that, and the first way was just to use the dead weight of water to push a wheel, and that's exactly what a wheel was. But of course, that has its limitations. They're not very efficient, and turbines developed. Turbines use a different method. The perhaps most successful and efficient turbine is the Pelton wheel that came along in the 1870s, and it uses a jet of water aimed at some buckets, and it's what's called an impulse turbine. It can use the kinetic energy of the water and extract that energy as rotation. Later, of course, we've got things called reaction turbines that are able to extract both the kinetic energy and the pressure energy from it. But given this came from a whale, we should be able to turn it into a turbine blade, point a jet of water at it, get it to rotate and extract some energy out of it, or at least that's the idea. So in order to explore that idea, what I've done is create this turbine blade. It's just a smaller version of this. So I've taken this and chopped it off there, shrunk it down a bit, and stuck it onto a PC fan. PC fans are great things for testing because they're really easy to turn into generators. All you actually do is snap off the blades, take out the electronics, and solder a couple of wires to the coils you'll find inside. There are quite a few guide videos on how exactly to do that, and I've done one myself, so if you're interested and don't know how to do that, just leave a message in the comments and I'll link to those videos explaining how to do that. But it's really easy to do. So what I've done is I've taken this, and there's a little indentation on the reverse side that exactly fits on there. That's an 80mm PC fan, incidentally. And I've glued that on and glued it to this backing. It's just a bit of backing board to hold everything stable. And what we're going to do is take this, point a jet of water, and see what happens. Okay, we brought it outside. Let's turn the garden hose on it and see what happens. I mean, partly we know what's going to happen. I'm going to get wet. Okay, that was cold. Now, it definitely worked as a turbine. I couldn't tell you which kind of turbine it was, whether it was impulse or reaction. But apparently, when the water hits that blade at the point of the tubercle, the flow is separated, and that's part of why the drag decreases and the lift increases. Now, these are beginning to creep in everywhere. You're seeing them in wind turbines at the moment. They've been starting to be put onto wind turbines and supplied as a kit for you to modify your own wind turbine. And you find them in slightly more bizarre places. They're on the kegs of surfboards, that kind of thing. But I've yet to see anybody looking at these in terms of water power generation. Now, we use a water jet, but I would think with something like the Wave Dragon, for instance, it might be an interesting way to look at something like that. Oh, the demand for sustainable and renewable energy resources has certainly intensified in recent years, probably due to the increasing global concern about climate change and the depletion of traditional fossil fuels. Now, among those various renewable energy options, wind power stands out as promising and eco-friendly as a solution, with the whole area probably being dominated by the traditional horizontal axis wind turbine. But these turbines, well, they're not without their problems. They're prone to lightning strikes, and of course, I consider them probably are quite lethal to the local wildlife. If they're not built properly, they have a terrible propensity to fall down, because they only really work if you stick them up there in the air. If they overrun, that is, get too fast, the consequences can be catastrophic. And every now and then, they have a terrible habit of bursting into flames for one reason and another. So although traditional horizontal axis wind turbines have dominated the wind energy landscape, there is a growing interest in vertical axis wind turbines as an alternative and potentially a more efficient option. Unlike their horizontal counterparts, VAWTs have a unique design in which the rotor is perpendicular to the ground. The vertical orientation allows the turbine to capture wind from any direction, eliminating the need for complex yaw mechanisms used in HAWTs to align with the wind. There are several designs of VAWTs, the most common designs being types of Diraeus, Savonius and helical designs. The Diraeus design, which is characterized by a curved blade arranged in a helical shape, is particularly popular for its efficiency and its aesthetic appeal. The major advantages of VAWTs are omnidirectional wind capture, simplicity and durability, low noise levels and scalability. And the disadvantages, or if you like, the challenges and considerations? Well, the first one would be startup torque and cut-in speed. VAWTs typically have a higher cut-in speeds and require a minimum wind speed to start generating power, and that can be a limitation in areas with lower than average wind speeds. The second one is efficiency at low wind speeds. While VAWTs are brilliant at capturing wind from various directions, their efficiency at low wind speed is generally lower when compared to HAWTs. And the final one are the aesthetics and the public perception, because although the unique designs of VAWTs can be appealing, some folks find them less appealing than the conventional HAWT with the familiar three-blade design. Public perception and aesthetics can seriously impact on the widespread acceptance of new technology like VAWTs. But generally, VAWTs are a promising avenue for harnessing wind energy with distinct advantages. However, more work is required. In the quest for more efficient and sustainable energy solutions, researchers and engineers are increasingly turning to nature for inspiration. Biomimicry is the practice of imitating biological systems and processes to solve human problems, and that's led to innovative designs across a whole range of industries, the notable example being the integration of whale tubercles into wind turbine design. Whale tubercles are small rounded protrusions found on the leading edge of humpback whale flippers. And these tubercles are not merely pretty, they serve a critical purpose in optimizing the whale's hydrodynamic performance. Researchers revealed that these bumps alter the flow of water over the flipper, reducing drag and increasing lift. And this, of course, makes it a natural adaptation. And that's captured the imaginations of science and engineers seeking to enhance the efficiency of man-made structures particularly wind turbines. So in order to look at all of that in a practical way, what I've done is I've created this. This is the blade for a VAWT that we're going to put together. That one is without tubercles and that one is with tubercles. Now it's a very simple design, it's just 3 blades, and you'll find this in Thingiverse, so the link is in the description below if you want the files. But there are 3 blades without tubercles, and we're going to arrange them into a VAWT, and to do that we've got these 2 tops and bottoms, and they've got holes in them at 120 degrees and a central hole, and then you should have 8 of these and 1 of these. 6 of these just get jammed into those holes. You can glue them in with cyanoacrylic glue, and we do that with the top and the bottom, and then once we've done that we stick those into the blades, making sure that the leading edge is all the same direction. When you've done that, that's what you'll get. Now you'll have 2 more at the same length. One goes in from the top, one goes in from the bottom, leaving a little bit stuck out. Then you'll have 2 of these, they go onto there, and we do exactly the same with that one. When you've got that far, you'll find a shorter one. These are 100mm long, this is 75mm long, and it goes directly in the middle like that. And of course what we need is a couple of couplers. So you slide a coupler on there, and then another coupler on that side, then you pop that in between, put a bit of glue on there and slide it up so the coupler is halfway between the 2, and you do that both sides and that will hold it together. When you've done that, grab yourself a couple of 8mm washers and put 1 on each side, and then a bearing on each side. These are skater bearings, so they're 22mm by 8mm by 7mm thick, and they go on either side like that. And then we're ready to put that into the cradle. To make the cradle to hold this, there's a cradle base and there are 2 uprights, a bit of acrylic glue, and stick those in there, and then we'll be able to stick them together and that'll make the cradle. And then our rotor just clips into the cradle. Now I put a couple of extra washers there to space it out a little bit because it was catching, but we're going to turn a fan on it to see how quickly it will turn in that fan speed. And to measure the RPM, I've put a strip of reflective material there. It's just a reflective aluminium strip because we're going to use this, which is a digital tachometer, and it works by bouncing the light off that strip, so it'll count 1 rotation. So we're ready to go. Now the only other thing we've got to do obviously is exactly the same thing, but this time with the tubercles. Okay, so I've set up my fan, we'll turn it on and we'll see what happens. Now commonly these things don't start to spin all by themselves. You have to give it a little flick. It's one of the drawbacks of this style. Let's give it a flick. So we're getting about 100 RPM. And here's my tubicle version all put together. And we've got the same metallic strip there. We're going to clip it in the cradle and see what happens. We're getting 149 RPM, which is pretty cool, eh? So research is showing that integrating these tubercles into VAWT has 4 serious advantages. The first thing is it increases efficiency at low wind speed, which is of course one of the banes of VAWTs. The next thing is it reduces noise and vibration, and perhaps a knock-on effect of that is it increases durability, giving them a longer life and reducing maintenance costs. So the last thing is it increases energy capture in turbulent winds, and that is one of the key advantages because these kind of turbines really should be used in urban environments where the wind is always turbulent. Now I've put it this way just to test it, but it doesn't really matter if it's in that direction or if it's stood upright. in that direction. It's easier for me to put it into a cradle to test it for you and to have a quick example, but there's a lot of ongoing research based on this biomimicry, and tubercles are really looking like they're going to make a significant contribution, so I thought I would do a video of it. Now of course these files are available if anybody wants them, and if you just want the blades by themselves to save you drawing them, then just take the blades by themselves. I hope you enjoyed the video. Thank you very much for watching, and please do remember to like and subscribe.